Good evening, everyone. So, welcome to our week 6 live session for the course Basic Environmental Engineering and Pollution Abatement. I'm Niketa. I'm a PhD scholar at IIT Madras, and I will be your TA for the live course, for the live sessions. So, before I start, I want to ask you if you have any questions from the previous class or from this week's lectures that you have watched. Okay, so if there are no doubts, then we will start. So, usually, what I do in these sessions is I will be teaching a brief overview of whatever content you had already seen in week 6 videos, and then we will be going over some questions and answers. Is that fine?
That's good.
Okay. Okay, so I'm assuming that you've watched today, week 6 lectures. So we'll start with sources of drinking water. What are the available sources of drinking water? Where do we get our drinking water from? From where do we get our drinking water?
Rivers,
Sorry?
rivers,
Okay, river.
lakes, reservoirs,
So rivers and lakes come under which category?
surface water.
Yeah. So broadly, the sources can be classified as surface and groundwater sources. So surface water includes rivers, lakes, sometimes springs, and so on. And then there is groundwater. So once we take water from these sources, they need to be treated before they are supplied for drinking. Because they may have some impurities, they may be polluted. So we need to remove all those pollutants. So how do we do that? We'll be seeing in detail. So the treatment process, first we take the water from the source and then we screen it. Screening is just making the water flow through some grid or some screen so that any floating particles or any big sized particles, maybe like leaves or plastic bottles, etc., all of these get removed. And then we do coagulation and flocculation. and then sedimentation. And after sedimentation, we will be doing disinfection. And once the water is completely disinfected, we can store it, or we can get directly distribute the water. Okay. So I've already explained to you what is screening. So screening is where we remove all the big particles, floating particles in water, like leaves or paper or even some plastics. So whatever floating objects are there, they are removed in screening. And then comes coagulation and flocculation. So why do we do coagulation and flocculation? Any ideas? Any guesses?
To collect waste particles.
Waste particles. Can you
Yes.
elaborate on that?
I mean, in floculations, we like convert into like flocks, small flocks, which are of 100 micrometers.
What is converted into flock?
Tiny, tiny particles.
What are they called? So in the previous few classes, we have seen the different types of solids in water. So can you guess which kind of solid will get removed in coagulation and flocculation? Okay, first tell me what are the solids that we saw in the previous class? Types of solids.
Suspended solids, dissolved solids.
Okay. Of these, which will be removed in coagulation and flocculation?
Dissolved solids,
Why do you think so?
because suspended solids can be easily separated during sedimentation.
Okay, so sedimentation is only for particles that can settle down. So if the particles are heavy enough, they'll come down because of gravity. So do you think particles that remain suspended, will it be possible for it to settle down? Imagine you have turbid water, not turbid water, you have suspended solids in water. Then will it be possible for it to settle down?
Hardness can be an example. So if we raise hardness can be the example of suspended solid.
Hardness.
Yes,
How?
because carbonates of calcium and magnesium.
No, those carbonates are going to be dissolved. See, when you have suspended solids, they are going to be suspended in the liquid. They are not going to settle down. They'll just remain suspended like this, no matter how much time you give. Okay? So they'll remain suspended, and that will make the liquid look turbid. So you cannot remove them easily unless you go for coagulation and flocculation. That is why we go for coagulation and flocculation to remove suspended solids. And how do we do this? So these suspended solids are suspended because of their surface charge. So when we go for coagulation and flocculation, what we do is we remove the surface charge and we make them neutral. So imagine you have a positively charged particle and all the particles are positively charged. So there is one more particle over here. So both of these repel each other and that's why they don't come together. But when we do coagulation, we remove these surface charges, make them neutral. So when they are neutral, there is no repulsive force. There is no repulsive force acting on them. And because of van der Waals force of attraction, these particles get attracted towards each other and come closer. So when these two particles come closer, they fuse together, they become a bigger particle. So what happens when the size of the particle increases? Its weight also increases, its mass increases, and because of that, it becomes easier for it to settle down. So when you have smaller particles, they are just going to remain suspended. But when you have larger particles, the weight of the particle increases, because of which the force of gravity will act and the particle will settle down easily. So that's what we do in coagulation and flocculation. We add some chemicals to neutralize the charge.
In coagulation, we are adding chemical coagulants. But what about flocculation? What we are adding?
Can you guess what is flocculation? What are flocks? Have you heard
When
of the
this
term flocks?
when this tiny particles come together, they make
Yeah.
denser flock
Yeah,
and they
so that's
settle
what.
down.
Yeah, those are flocks. So from this, can you guess what is flocculation? Flocculation is forming flocks, so making it easier for the particles to flock together. So what we do in flocculation is we will stir the tank. Like you already have added some coagulant to make sure that the particles are coming together, and then you stir it gently. So you have a stirrer in the middle, and you have some blades. So you stir it gently, and because of the stirring action, the flocks will come together. So it will be easier for the particles to come together and form
And
flocks.
form flocks. It means just like a clarifier.
See, clarifier, yeah, something like that.
In clarifier as well, the turbine
No,
rotates
in the
slowly.
clarifier, we have on top, we have a skimmer on top. So that will remove all the oils and stuff. So this is just for giving a gentle mix so that the flock can form. So once the flock gets formed, we allow it to settle for some time in a sedimentation tank. That we will see in the next part. So usually the size of these flocks are from 1 to 100 micrometers. So this process removes color and turbidity. And what are some of the coagulants used?
alum,
Yeah, alum, ferric chloride, ferric sulfate, and some polyelectrolytes. Now, these polyelectrolytes, they are just polymers, so they can easily bond together different particles, so their size will increase. So usually when we add alum, alum is Al2 SO4 thrice 14H2O. So when we add alum to water, this reaction happens. So it gives out 3Al plus. So this Al3 plus, it is in the form of aluminum hydroxide. So this aluminum hydroxide will interact with the colloids, and then it will neutralize the surface charge. But if we are using alum, then the optimum pH for the reaction to happen is 5.5 to 6.5. And for the flocculation, we will do a flash mixing. For 1 to 2 minutes, we will be mixing rapidly. And then after that, slow mixing is done for 20 minutes. And after this, the flocks are allowed to settle down in a sedimentation tank for 3 hours. And by the way, a clarifier is also called as a sedimentation tank. So I think you got confused between flocculator and a sedimentation tank.
yes, ma'am.
Okay, so first there is rapid mixing of alum, followed by flocculation, and then it is allowed to settle down. Now for settling, uh, the settling principle follows Stokes' law, where the settling velocity or Vs is given as so Vs is your settling velocity. Rho s is particle density. Rho is the fluid density. So by particle density, we mean the density of the colloid, and rho is the density of the liquid or water. D is the particle diameter. And mu is the dynamic viscosity. And then there is another kind of velocity which is called the overflow velocity. Now, these two are in opposite directions. So your settling velocity, imagine this is your tank. So the settling velocity or Vs is downwards, whereas the overflow velocity or the velocity with which the water flows out of the tank after settling is usually upwards and sidewards. So your outflow velocity is upwards because it has to carry the water outside the tank. So these two are in opposite directions. Now the settling will happen under what circumstance? If you have a particle that you want to settle, then which velocity should be higher?
I think settling velocity should be higher to get the particles settled down quickly.
Yeah, so for settling to happen, your settling velocity should be higher than the overflow velocity. So the overflow velocity is given by Q by AS, where Q is the flow rate or the amount of the volume of liquid flowing out per second. So that is given in terms of meter cube per second. And this is the cross sectional area. So the cross sectional area will mean the surface area of the tank. So if you have a tank of so imagine this is in 3 dimensions. So this is the breadth B and this is the length of the tank. So then your cross sectional area, which is AS, is given as B into L. Next, coming to filtration. So, what kind of particles are removed in filtration?
The particles which are greater in size than pore size of filter paper.
Yeah, that is fine, but I'm asking with reference to like what will be the size of those particles. You don't have to be exact.
Soluble solid.
What?
Soluble solid.
I didn't get you.
Settleable solid.
Settleable solids. If solids were settleable, then why will we go for filtration? We could have just gone for a sedimentation tank or maybe for coagulation or flocculation, right?
Floating particles.
So I just said that screening is used for removing floating particles. Why is filtration used?
For more tiny particles to
Yeah,
separate
for
out.
particles which are smaller than that which can be coagulated, those are removed by filtration. So that is used for very small particles. And in a filter, we have something called a loading rate. And this loading rate is given as VA. So the loading rate equals to Q by cross sectional area. So here the loading rate is also known as phase velocity, and the units for this is meter cube per day meter square. So we'll see what this is in detail. So you imagine if there is a filter like this, and assuming that this is your filter media, okay, and you have water coming from the top, okay, and this is going to be the cross sectional area of the filter. So if you have this is the side view. So imagine if this is actually a circular tank from the top, something like this. So
And the units will be meter per day.
liters per day.
Meter per
How?
day. Yeah.
Meter per day. Yeah.
Yeah.
But for understanding, we write it as meter cube per day per meter square. I'll tell you why. So if you just say meter per day, that is just velocity rate. That is not loading rate. So loading rate is how much volume of water passes through the filter per meter square of that filter per day. Understood?
Yes, ma'am.
Okay, so imagine you have a circular filter like this, and the diameter of the filter is D. So what is the surface area? What is the surface area of the filter?
Pi D.
Pi D. Are you sure? So the area is pi d square by 4. So the area of the filter, diameter is D. So area is pi d square by 4. Now, your loading rate VA is Q by AS. So, your surface area or the area through which your water is going to flow through is this. So, water is going to flow through, like this is the top view. So, side view is going to be something like this. So, the water is going to flow through this circular area. Um, your flow rate or the rate at which the water is flowing through is given by volume by time. So here we assume that since it's a water treatment plant, so we will be looking at how much water is flowing through per day instead of per second, because per second the volume may be less, but we look at for big structures like water treatment plants, we usually look at how much volume flows through per day. So that is why we take Q as meter cube per day. And for surface area, we have already the formula is there. So whatever area of the filter is there, that you have to find out. So when we divide these two, this is in meter square. So this is going to be meter cube per day per meter square. Now, the reason why it is represented like this is because we want to know how much of water is flowing through this filter every day, and by how much surface area. So, you already know the flow rate. So, if you divide that by the surface area of the filter, you will know that how much water is passing through the filter each day. So, that will tell you how much water is getting treated by the filter every day. So there is one disadvantage of using a filter. It's that these filters usually have pores, right? So these pores can get clogged over time. So most of the time it's like some particle may sit and it will not move. So whatever water is incoming, so that will not be able to pass through. So backwash must be done. So what is backwash? Imagine you have a filter like this. Water always flows from in one direction, say top to bottom. So instead of when your pores inside the filter get clogged, instead of top to bottom, we make the water flow from bottom to top. So what happens then? Whatever clogs are there, they will get released. So these clogs will, I mean, whatever was clogging, whatever sediments were there, these will come to the top, these will break and come to the top, and then they will be removed. So backwash should be done in every 10 to 15 days. Okay, coming to the different types of filters. So broadly we have two types. First one is the slow sand filter. Second one is the rapid sand filter. So slow sand filter, as the name suggests, is very slow, and whereas the rapid sand filter usually flow happens because of some pressure inducing device like a pump, and it creates a vacuum because of which the suction happens and the water flows through the filter rapidly. Whereas in slow sand filter, the force acting on the water is just gravity. So gravity only initiates the flow through the sand. Whereas in a rapid sand filter, it could be vacuum plus gravity. So slow sand filter will be useful when we have no, a slow sand filter is actually more efficient because it has the capacity to remove small particles, very small and tiny particles. It has about 99.9% efficiency, whereas a rapid sand filter is not so efficient. It has about 94 to 95% efficiency. The reason being that in a rapid sand filter, the filter particles, the pore size is usually bigger. So you have bigger sized pores, and also the flow is not happening because of gravity, it is happening because of vacuum. So because of vacuum, sometimes even the solids get pulled through the pores and may not be retained on the pore itself. So when you have a large force, you have particles. I mean, when you have a filter bed like this, and your water is incoming, and there is a small particle, tiny particle like this. So because of vacuum force, the particle may fall through the pores and it may come down. So that's why the treating efficiency is not so high in a rapid sand filter. Then comes ion exchange.
Ma'am, slow sand filter is energy efficient.
Yeah, that is also there. It requires less energy, but the disadvantage of
It
slow
is
sand
because
filter is
we
that
are using vacuum and that requires external energy.
yeah, right. So let me finish. So a slow sand filter, the disadvantage is that it requires a large area. So when you have a slow sand filter, because you cannot treat large volumes of water in a given time. So because the flow through the sand filter is very slow, you need to provide a larger area to compensate for the loss in speed. So when you have a rapid sand filter, water is going to pass through the filter rapidly, so more volume of water can be treated quickly and with a limited space. Whereas if you go for a slow sand filter, we need a large area, because we need, if you have the same volume of water, it's going to take a longer time for the filtration to happen. So that's why we need a larger area. Coming to our ion exchange. So what is removed using ion exchange?
Hardness.
Yeah. So it is used for removing hardness. So ion exchange usually has some resin. So the resin is already positively charged. It's got cations in it. So the cations in the resin will replace the calcium and magnesium salt present in the hard water. So, like I have told you before, hardness is caused by the presence of calcium and magnesium salts. So, if you pass the water containing calcium and magnesium through the ion exchange or the ion exchange resin, so which is positively charged, uh, then what happens is that the calcium and the calcium and the magnesium in the water will be replaced by the sodium in the ion exchange. So this ion exchange is made of sodium ions. So these calcium and magnesium containing water, when it passes through this ion exchange membrane, so these cations will be replaced by sodium, and the water coming out will be free from calcium and magnesium, but instead it is going to have sodium. So whatever calcium and magnesium was there, it is going to be retained on the membrane itself. So in this process, what happens is, over time, whatever positive ions or sodium ions were there initially, all of it is going to be replaced by calcium and magnesium. So with time, the sodium is going to get depleted and it is just going to be calcium and magnesium. So what happens if the membrane is completely filled with calcium and magnesium? Then it cannot replace the calcium and magnesium present in the water which is flowing through it. So that creates a problem. So that is why when the ion exchange membrane is exhausted, by exhausted I mean the sodium ions run out, then we have to make a solution of brine or sodium chloride, and we have to make it run through the ion exchange membrane so that whatever sodium ions were depleted, they get replenished. So, if you pass a solution containing sodium chloride through the through the membrane, then these sodium ions will again come on the surface of the ion exchange membrane, and they can easily replace the calcium and magnesium that is coming in with the water. Okay, then coming to disinfection. The first method of disinfection is chlorination. So, what happens in chlorination?
This brine solution means sodium chloride, right?
Yes.
And as you said, that sodium ions will replace calcium and magnesium. So what about the chloride ion, Cl minus?
Yeah, they will also. I mean, if the solution contains, if the inlet solution contains chlorine, then that will not be replaced. But if it is containing something else like carbonate, then that will be replaced.
Okay.
But we are not concerned about that. We are only bothered about the positive charge because uh, calcium and magnesium chloride will also cause hardness. So that is why it is important to replace the cations in the solution mainly. We are not concerned about the anions in this method.
Okay. Chlorination means adding of chlorine tablets to treat the infected water.
Yeah, what happens then? What is the reaction?
Killing of pathogens.
No, I'm asking what reaction happens. You said we have to add chlorine. What happens once we add chlorine?
H2O plus Cl will form hypochlorite, HOCl.
Yeah. So chloride with water will form hypochlorite and H plus and Cl minus ion. So this HOCl or hypochlorite is the main disinfecting agent. The next one is ozonation. So in ozonation, like there is a difference between chlorination and ozonation. So in chlorination, we saw how the disinfecting agent is produced. So this chloride will react with bacteria and it will deactivate the bacterial cells. And the disadvantage of this process is that it will produce sludge. or it will also sometimes produce disinfectant intermediates. So, if other than bacteria, some other pollutant, organic pollutant is there, then this hypochlorite will react with that organic pollutant and it will produce some byproduct. So, those byproducts are harmful for our health. So, this process of chlorination is not so preferable these days because there are so many issues associated with disinfection byproducts or DBPs. So it's important to understand that if there is organic pollutant or if there is any organic matter going to be present in the water that needs disinfection, then it will react with the chlorine and it will produce some disinfection byproducts. So that is supposed to be avoided. So that is why we go for ozonation. So in ozonation there are no harmful byproducts. Because even if there are organic pollutants, they are going to be completely mineralized and converted to carbon dioxide and water. And that is why ozonation is a better technique than chlorination. So you don't get any byproducts, and there is also removal of taste, color, and odor. Now, this was about surface water. So, if we have groundwater, then we need to modify the treatment process slightly. So, groundwater usually has hardness, minerals, and pathogens. So now we saw how water is treated. So we will be seeing about the treatment of domestic sewage or domestic wastewater. So the domestic wastewater can be treated in two ways. First one is by sewage treatment plant or STP. And the second one is by using septic tank, but these days it is not so prevalent. So in the older days, we used to have homes with septic tanks where on site whatever waste water was generated, that was treated in the same place where it was generated. And for this, we don't need any sewers or specialized pipelines to carry the wastewater from one place to another place because the treatment is done on site. Whereas in STP, it is both centralized and decentralized. So we need some pipelines to carry the waste from the source to the treatment place. And once the wastewater has been treated, it is disposed on the surface. Like we can go for gardening, or maybe we can even if it meets the standards, then we can even dispose the treated wastewater in a surface water body, like disposing it in a river or a sea or a lake. Now, industrial wastewater is treated in ETPs or effluent treatment plants. So there are two types of EPPs. If there is only one industry, then it is going to be a single EPP. Otherwise, it is going to be a common effluent treatment plant or a CETP. Now, a CETP is used when there is a cluster of industries. So we look at how an STP works. So first we have the raw sewage. The raw sewage will have a lot of floating pollutants. It may have plastic bottles. It may have cans.
Have a lot of cans.
It may have maybe some uh, what to say, clothes or anything that floats. So all of these need to be removed, and for that we go for screening. So for this we use a bar rack. Now a bar rack is used for screening to remove any floating particles. And once the particles are removed, the water is then passed through a grit chamber. Now, what is a grit chamber? It is basically like a sedimentation tank where you allow stones or some small particles to settle down. So, whatever grit is there, like maybe you have glass or maybe some small pieces of stone or some other solids which will block the flow of the plant, and such particles need to be removed before they even enter for the next few processes. So that's why we allow the wastewater to settle down in a grid chamber. And then we have the equalization tank. So a equalization tank is used when
Adjusting pH.
huh?
Adjustment of pH.
Not really. So when you have a large sewage treatment plant, and the flow is not going to be uniform throughout the day, right? Because in the morning, many people will be getting ready to go for office, so there will be a lot of washing, there will be a lot of uh, bathing, showering, and all that. So during specific periods of time, like especially from let's say 8 a.m. to 10 a.m., there is going to be a lot of sewage that is coming out because there's going to be cooking and cleaning, washing, bathing, showering. All of this is going to happen. And after 10 a.m. to maybe say 2 p.m., there is not much sewage which is generated. So this is a lean period. So during lean period, the flow that comes to the sewage treatment plant is going to be less. Okay, but we have designed the sewage treatment plant for uniform flow or constant flow. So what do we do in that case? What we do is when there is high flow, especially in mornings and evenings, we store the excess in a equalization tank, and when the flow is lean or when there is very less flow, then the stored sewage water is released. So an equalization tank is used for that purpose, to equalize the flow or to maintain a constant flow. Plus,
Okay, ma'am.
also, it's when we have sewage with different characteristics, like maybe some will have a different composition, and some of them will have a high organic load, some will have a lower organic load. So, in order to make sure that the flow is uniform throughout and there is no shock that is coming into the system, in order to avoid that, we also, and for that reason, also use the equalization tank so that the flow is uniform, and also whatever organic load is there, whatever pollutant load is there, it's going to be uniformly mixed. So it maintains a constant flow. Now, these three steps, which is screening, drip chamber, and equalization tank, they will come under pre-treatment or preliminary treatment. So preliminary treatment includes screening, grid chamber, and equalization tank. Now then we go for primary treatment. Once we are done with preliminary, we will go for the primary treatment. So whatever sewage was there in equalization tank, that will be allowed to pass through a settling tank for primary treatment. So that is your primary treatment. Primary treatment has only one process, which is settling or primary settling. Now we go for the secondary treatment. So in the secondary treatment is where we actually treat the wastewater in different ways. So conventionally in many STPs, we do biological treatment. Because it is one of the easiest ways, and it is also highly scalable, and it is very much suited for sewage.
We use activated sludge process.
Yeah, that is also a biological process. So we'll see about biological process in detail a little later. There are different types of biological processes, and we'll see each of them. So secondary treatment is just biological treatment, or in biological treatment, what it means is we will use microbes or bacteria to treat the wastewater. So there are different types like ASP, trickling filter, or anaerobic treatment, all of that. So all of this collectively comes under secondary treatment process. So then is the tertiary. So tertiary treatment will include advanced processes like reverse osmosis, ultrafiltration, and all that. Once we are done with tertiary treatment, then we go for disposal. So by the end of the primary treatment, about 35% of biological oxygen demand, or the BOD, is removed.
Disinfection comes under tertiary or secondary treatment.
That is secondary.
Why not tertiary?
What is tertiary treatment?
Like advanced processes. So
Yeah.
disinfection.
Usually, STPs will only have up to disinfection or secondary treatment. So in tertiary treatment, we will remove any suspended solids, turbidity, or any color, etc. All that is removed only in the tertiary treatment. So that is most STPs in India just stop with secondary treatment, but tertiary is also necessary because otherwise it will be difficult to reuse the water.
Yes.
So if we are just going to use the treated wastewater for gardening, or if we are just going to dispose the treated wastewater in a lake or a river, then secondary treatment is more than enough if we
Okay.
meet the required standards. Otherwise, we need to go for tertiary treatment.
Okay.
So, in tertiary treatment, in secondary treatment, about 85% of BOD is removed. And in tertiary treatment, about 95% of BOD is removed. So we'll be seeing each one of these in detail. So first, we'll start with bar racks. So bar racks are used for removing large objects, like I said, floating particles, maybe pieces of cloth, plastic, or any solid waste that is floating. So that is why we use bar racks. And whatever, I mean, it's just going to be like a rack which is inclined, through which the water will pass through, but all the solids which are retained, so they will be collected in a separate hopper. So water will pass through easily, but whatever solids are retained, they will be allowed to fall in the hopper. And then there is grit chamber. Grit chambers, like I said, is like a huge sedimentation tank where particles like sand, silt, small pebbles, usually solids which are heavier than organic solids, or metal pieces are allowed to settle. Now, why this is done? Because water needs to be pumped to various units inside a sewage treatment plant, and the presence of these solid particles will interfere with the pumps. So it will easily damage the pumps. So that is why, to prevent the wear and tear of pumps, we are going to remove these particles in advance. So that's what it is. And sometimes these grit chambers can be aerated also. So the advantage of an aerated grit chamber is that we are bringing the secondary treatment process here itself in this step. So aeration introduces oxygen, and in the presence of oxygen, the bacteria will start decomposing the waste little by little. So that's a grit chamber.
I think in aerated grid chambers, there are also like organic materials that can be treated.
Yeah, that's what I said, right? Bacteria can decompose the waste in an aerated grit chamber. It can start decomposing the waste.
So further, they will not require treatment, right?
No, see, grit chamber is where the water is going to spend minimal time, like maybe a minute or two. That's it. It's not going to spend a lot of time, like in a sedimentation tank or in a activated sludge process. There, it will spend about 1 or 2 hours, but here it is going to spend only a couple of minutes. So, in that time, if aeration is given, then it will just start the process. It won't make it like it won't be complete in a grid chamber.
Okay.
Then we have the equalization tank. So, like I said, it's used for regulating the flow. So, if you have periods of high flow or a lean flow, then we can regulate the equalization tank accordingly so that the same flow is maintained throughout the day. And it also prevents the wastewater from turning septic because we will be continuously mixing the water, so that will allow some aeration, so it will prevent anaerobic conditions from setting in. Okay. Then we have the primary sedimentation tank.
How much flow should be maintained while passing the water from grid chamber, aerated grid chambers, especially?
Uh, Aerated grid chamber maybe about uh, 0.5 meter cube per second. So then we have a primary settling tank where we remove the settlable solids and floating substance. So just like in a water treatment plant, here also we have a sedimentation tank, but we don't do coagulation and flocculation here because the amount of solids in this water is very high, so we won't be able to supply as much chemicals to remove the solids in this process. So that's why we leave it to the bacteria to work on the solids. So here it is just for removing the settlable solids and floating substances. And then there is the secondary process or the secondary treatment.
Septic tank and sedimentation tank are both the same, right?
No,
What is the difference?
you tell me what happens in a septic tank.
I think they are both same
Why do you think so?
because initially we use septic tank before treatment.
I don't understand you. Did I mention septic tank in any of the at any point in the treatment process? Is septic tank mentioned anywhere here?
No, I mean it can be the another name for this.
You tell me why you think so. What happens in a septic tank? Okay, what is septic? A septic tank is where
I'm
anaerobic
confused.
process takes place, right?
Okay.
So previously we used to collect the domestic sewage and treat it on site in a septic tank. So the process was entirely anaerobic. We used to close the septic tank completely. It was completely sealed, and whatever sewage was coming, it used to get treated in anaerobic conditions in the absence of oxygen. So there itself, the solids used to settle down, and whatever organics were there, they would be converted into carbon dioxide and methane, and there will be a small outlet for releasing the gas. So that's how a septic tank worked. So it is an alternative to the secondary treatment process, but it is not an alternative for a sedimentation tank.
Okay, ma'am, got it.
See, a sedimentation tank is where you allow the solids to settle down, right? But a septic
Yes.
tank is entirely different. In a septic tank, the organic waste is completely treated under anaerobic conditions.
Yes.
Whereas in a sedimentation tank, we allow the solids to just settle down. The settled solids are removed, and after the sedimentation tank, the water goes to the secondary treatment.
Secondary. Yes.
Yeah. So in the secondary treatment, we usually go for biological process. So biological process removes BOD and suspended solids. Now, there are certain requirements of biological process or secondary treatment. The requirements are a high density of microorganisms or microbes, high oxygen levels or aeration, and then we also require proper mixing to happen so that the oxygen level is uniform throughout the tank, and there should be no toxic substances, because if there is something which is toxic to the microbes, then all of the microbes or all of the bacteria will die. So we don't want to have any toxic chemicals which will be harmful for the microbes. So these are the requirements of biological process. There should be a high quantity of microbes because they are only going to degrade the pollutants, so their population is should be high. And then we need to have high oxygen levels because otherwise the microbes will die and anaerobic conditions will develop. So
ma'am, this STP, we get no substances, all right, but in ETPs, we can get toxic substances.
yeah, so there the treatment process is different. It won't be it's not necessarily biological.
Okay, but we use biological treatment there also.
Yeah, that's what I said. It need not always be biological. It can be biological if there are no toxic substances.
Okay, but what is then used instead?
There can be other methods like maybe if there are no biological solids, then we can directly go for coagulation, flocculation, or filtration, and all of these processes. Or maybe even for complete breakdown, we can even go for electrochemical methods, advanced oxidation processes, and so on.
Okay.
But usually we go for biological processes, mostly 90% of the time in ETPs. And before bringing the before bringing the water for biological treatment, we have to ensure that whatever harmful chemicals are there, they are removed.
Yeah, in STPs, we are having less chance of getting toxic substance.
Yeah. I was saying about ETPs. In ETPs, when we go for biological treatment, it is necessary to remove toxic substances, which will be harmful for the bacteria.
Yeah.
Okay, and then whatever sludge is formed, it is separated from the sedimentation tank, and also after secondary treatment, whatever sludge is there, it is separated. So then we have the secondary sedimentation tank. The reason why we go for a secondary sedimentation is because after the biological process, there will be dead bacterial cells mostly, which require removal. So they will form a solid known as sludge. So this sludge will settle down at the bottom of the tank and something like this. So sludge will settle towards the bottom. So whatever treated water is there, it will pass through the sedimentation tank for the it will pass to the next process. But this solid sludge will remain at the bottom, so it needs to be removed, and the sedimentation tank will get refilled with a new batch of water. So sometimes this can also be continuous, so there will be continuous inflow and outflow of water, and periodically whatever sludge is formed will be removed.
This sludge can be collected, ma'am, and used for drying sludge or sludge
Yeah, we'll see
dewatering.
about that later, what we do with sludge. So right now our focus is on water treatment. So we'll see what happens to the wastewater as it passes through different treatment processes.
Yes.
So till now we have seen up to secondary sedimentation. So once the sludge is removed, the clear water is separated. And why we require this is because after the secondary treatment process, a lot of solids or sludge will be generated. This is mostly just dead bacterial cells. So the bacteria will feed on the organic matter and it will multiply. So once it reaches the end of its life, it will die, and that's when sludge is produced. So why that happens is because when the microbial population goes beyond a certain limit, it will enter a stage where it will eat itself. Like other microbes will eat each other. So and then there is so what happens is when you have organic load and all the microbes and bacteria will feed on the organic matter and they'll continue to grow. So over time, the number of microbes is going to be higher than the organic matter present. So once all the organic waste is completely eaten by the microbes, so they will start eating themselves. Because their population is high, we have larger number of microbes when compared to the organic waste. So in this condition, what happens is the microbes will start eating themselves and they all die. So the sludge is mostly just dead bacteria or dead bacterial cells. Okay, so then once we finish with the sedimentation, secondary sedimentation, we go for tertiary treatment. So tertiary treatment can be adsorption. So whatever impurities were still not removed in the secondary process will be removed in the tertiary process. This is done mainly for removing micropollutants, pollutants that are whose concentration is in micrograms per liter. Those are known as micropollutants or emerging contaminants. Those can be removed by adsorption, usually on activated carbon. They can also be removed using filtration or other advanced processes.
Ozonation can be under tertiary treatment.
Why? We just saw that ozonation comes under disinfection, and disinfection is a secondary treatment process. So why will it come under tertiary? Okay. So this was a brief about various processes in wastewater treatment. Now we will see about settling. So settling was done in water as well as wastewater treatment. So there are some factors which affect the settling process. First one is the density of the particles. And then the particle size. Temperature. Turbulence. Stability. Bottom scour. And flocculation. So the density of the particle size, the temperature of the water, because temperature directly affects the density of the liquid, and so if it's going to be low density liquid, then your solids will settle down easily. But if the density is going to be higher, then it will be difficult for the particles to settle down. So that is why temperature plays a role here. And also the turbulence. Turbulence is the disturbance created in water when it flows. So there could be some small particle which is obstructing the flow of water, so that creates a turbulence. So when turbulence is created, then the particles are obstructed from flowing in the continuously in the same direction. So if there is a lot of turbulence, the particle may not fall down due to its own weight. Instead, it will move in other directions. So when the water is highly turbulent, or when there is no laminar flow, then this will happen. And then the stability and how much bottom score we are giving. Like sometimes when there is a sedimentation tank like this, and over time the particles get settled down, and what happens is, imagine this is your tank and this is the bottom where solids are settled. So sometimes due to the flow of water, if the settled particles are not removed, then with the water flow, these settled particles will also rise up, and they will repopulate the water in the tank, and they will also come down along with this. So this needs to be avoided. So this is bottom scour. And then the rate of flocculation, or the rate at which the flocks are formed. So if the flocculation is good, then there will be good settling. If flocks are not well formed, then they won't settle down. So there are different types of settling. Type 1 is discrete settling. So in discrete settling, the particles will fall down at equal depth in equal time. Okay, coming to discrete settling. So in discrete settling, this is the most. Am I audible?
Yes, ma'am.
Yeah. So this is the most simplest form of settling, where all the particles are distinct and discrete, meaning they are all separated, and there is no flocculation or there is no combination of particles together. So all of them are discrete and distinct from each other, and it is assumed that if a particle is if a few particles are present at height h, okay, so let's call it h1. So if these three particles are in the same height, then it will take the same time for all these particles to reach the bottom. But if there are other particles at height h2, then they are going to reach the bottom at a slightly lesser time, because they are already downwards and it is going to take them very a lesser time compared to particles at height h1. So this is discrete settling, where we assume that if particles are at the same depth from the surface, then they are going to fall at the same time. So here it is equal depth in equal time. Is this clear?
Yes, ma'am.
Then we have type 2, which is flocculent settling. Okay. So here we assume that the particles come closer together, okay, and they form big flocks, okay. So we take the height of these particles as h1. So at this height, the particles, some of them are distinct and some of them are forming flocks. So what happens when they form a big flock like this?
It will get settled down.
So compared to the other particles. So if you have particles which are forming a flock like this, which will settle down faster, this one or this one?
which is higher in density.
Yeah, so it will fall down faster. So the velocity with which the particle is coming down, which has formed a flock, it is going to be higher than a particle which does not form a flock. So here it is assumed that now with increase in depth, the velocity is also increasing, because at this stage it is still a particle having a small flock. Now as it comes down, it will meet other particles and it will form a bigger flock. So a bigger flock will have a even more velocity than a smaller flock. So your velocity is actually increasing with depth due to coagulation. So in flocculent settling, the particles combine together, they form a flock, and their velocity increases as they go down. Now compare with discrete settling or type 1 settling. Here, all the particles had the same velocity from top to bottom. So if your if it takes time t1 for some particle at h1 to reach the bottom, then that velocity is going to be the same. So until it reaches down, the velocity of that particle is going to be the same. But here, the particle initially it was small, but as it comes down, it is growing bigger and bigger. So as its size increases, its settling velocity is also going to increase because it has a higher mass now, and your gravitational force is going to increase because of that. So your velocity, the velocity at which the particle is settling down, will also increase. So here the velocity increases as the depth increases. So that happens because of coagulation. And then there is type 3 or hindered settling. So in hindered settling, the velocity actually reduces because the particles interact with each other. How?
Ma'am, repeat the question again.
Yeah, I'll explain. So if you have larger particles and they are going to coagulate and form even more larger particles like this, and there are so many of them, so it is no longer a free flow, right? So this particle does not have a clear pathway, so it has to collide with another particle at the bottom, and that will reduce its velocity. So it's not going to have a uniform velocity throughout. Maybe initially it will have one velocity, and as it coagulates, as it flocculates, its velocity will increase, and as it interacts with other particles, again its velocity will change. It will decrease. So this is hindered settling, where your particles hit each other, and because of that, their velocity will reduce. And then there is type 4, which is
I think in hindered settling, they will form piles.
what?
I think in hindered settling, the particles will come together and form a like mountain.
Mountain.
Yeah, I mean step by steps, one on another. I mean,
So in hindered settling, your velocity is reducing because your particles are hitting each other, and because of that collision, there is going to be reduction in velocity. So because of that, your initial velocity of the particle is going to decrease.
yes,
And then there is compression settling where the particles will form a layer. So this the particles are so densely packed now that it's like having a layer of them. So one layer will, the top layer will compress the bottom layer, and that will compress the layer below beneath. So these layers, the particles in these layers will come down at the same time. So they will, but before coming down, they will compress the. For example, this is layer 1 and this is layer 2. So the particles in layer 1 will come down at the same time. Particles in layer 2 will come down at the same time. But particles in layer 1 will compress the particles in layer 2. And if there are subsequent layers, then those layers will also be compressed. So in settling, it's also important to discuss about the critical velocity or scouring velocity. So scouring velocity is the velocity beyond which scouring will occur. So I've already told you what is scouring. So scouring happens when there is what flow this way. There is inlet and there is outlet. Then there is water flow this way. So there is inlet and there is outlet. So it is here, or maybe the outlet opening is here. So then what happens is constant inflow and outflow. And after some time, when there is sedimentation of particles here, if your flow velocity is high, it's so high that along with water, whatever solids had settled, even those solids will come and mix back into the solution. So imagine you have the water force is so high that it will carry the settled solids also, and it will move up. Am I audible? So this movement of particles or settled solids from the bottom to the top, and it's flowing out of the tank. So this phenomenon is called scouring. Scouring is basically moving the settled solids and uh, mixing them back into the solution, into the water. So the velocity at which this happens is very important because it should not be so high that scouring is induced. There should be water flow, of course, but it should not be so high that the bottom is also disturbed and scouring happens. So that is why we need to maintain the velocity such that scouring doesn't happen. So that velocity at which scouring happens is called critical velocity. So scouring is basically the movement of solids from the bed to the water and then flowing out. So should not be the velocity should not be so high that scouring happens.
or the water or the solids at the bottom get disturbed. So that is your critical velocity. And critical velocity or PC is given by this formula. Current critical velocity is given as VC, and beta is a constant. It's the gravitational constant, and this is the specific gravity, which is 2.65, and V is the particle diameter. Type of settling, sorry, secondary between processes. First one is the aerobic process. So, can you tell me what is an aerobic process? What's the difference between aerobic and anaerobic? Yeah, yeah. So, in aerobic processes, there is oxygen present, and whatever organics are there, they are converted into carbon dioxide and water. And in anaerobic process, this takes place without oxygen. So, whatever waste is there, it will be converted into methane and carbon dioxide. There are also, and these two processes use bacteria, by the way, aerobic bacteria and anaerobic bacteria. There are processes which use living organisms also directly. Uh, Plants, it's called phytoremediation. Yeah. So based on the type of microbial growth, the processes can be classified as suspended growth process. Here we have activated sludge process or ASPs, lagoons, stabilization bonds, and anaerobic digestion. Then we also have the attached growth process where you stripling filters, biological contractors or RBCs, and even fat bed reactors. And then we can even have a hybrid process combining both these groups. Okay. Sequential bioreactor or no, you're confusing between both. Sequential bioreactor is a type of batch process, so that can have suspended growth. Okay, so that is about the. It's not about the type of microbial growth. It's about the design. So it is a batch reactor, and usually we go for a continuous reactor. But if you're going for a sequential batch reactor, then it is a batch process where each of the processes takes place one after the other in the same place, in the same tank, or in a series of tanks. But all of them happen one after the other and in batches. So the same batch of water is going to be allowed to pass through each of the tanks, and only after it has passed through all the tanks will the next batch be allowed. So that is a batch type process, and I think you're getting confused between that and this. Yeah. So then, other than these, there are some conventional processes also like lagoons. So lagoons, they are not an STB, but they do the same function. So here also bacteria and algae will break down the organics. So what we do here is we will take the wastewater and spread it out to a large area. We call it a lagoon. So here, this is the side view. So here the raw waste is going to enter. So once it enters, what happens is that the algae present will convert the uh, sorry, first the bacteria will act. So the bacteria will act on the raw waste using oxygen and it will convert it into CO2. So raw waste along with oxygen, in the presence of oxygen, bacteria will convert it into carbon dioxide, ammonia, and phosphate. So now this carbon dioxide is going to be used by algae. That algae is going to give out oxygen. It's going to use the carbon dioxide for its own living and it is going to give out oxygen. So that oxygen is going to be used by the bacteria to break down the waste into carbon dioxide. And again, the carbon dioxide will be used by the bacteria. So this is going to continue like a circle. So this is called a facultative condition. So facultative is where uh, you have both aerobic and anaerobic happiness. So aerobic is this at the top where bacteria uses oxygen. But once the bacteria dies, it is going to give out dead cells. So all the dead cells are going to accumulate at the bottom. And here, once the layer of dead cell is formed, oxygen will not be able to penetrate. And therefore, this zone will become anaerobic. Okay? So in anaerobic, again there will be anaerobic bacteria, and these bacteria will convert the organics into methane, carbon dioxide, ammonia. So since both aerobic and anaerobic processes are happening together, so this condition is called a facultative condition. And this relationship between the algae and bacteria is called symbiosis, because both are living off each other. And there is gas exchange, of course. Whatever CO2 is produced, it is used by the algae. Sometimes there is escape of the CO2 gas outside, and sometimes there is also incoming of oxygen from the surface. So oxygen may not be produced by algae alone. It can also be produced. Oxygen may not be produced by algae alone. Oxygen can also enter the wastewater from the surface by mixing. So the advantage of having a lagoon is that it is low cost and the design is also very simple. And looking at anaerobic digestion. So here we'll be just looking at one type, upflow anaerobic sludge blanket or UASP. So here we have uh, an anaerobic reactor. Right? Once water enters, it will flow upwards. Wastewater will flow upwards, and uh, water flows upwards. Most of the solids will get retained at the bottom, and it will form a blanket. Okay, so this is called a sludge blanket. So it is not just made of solids from the wastewater. Uh, Whatever reaction happens, the bacterial cells also form the sludge. So they'll also come down and they'll form a sludge blanket like this. So over time, what happens is that when there is water inlet, the water coming in actually flows through the sludge blanket and goes to the. Initially, this blanket is not there, so there is free flow of water. But over time, when there is sludge formation, uh, there is a layer of sludge through which the water has to pass through. Okay, so this is the sludge blanket, and through which the water will pass through. And in this place, it will react with the anaerobic bacteria, and sludge will be produced. Now, again, sludge is nothing but dead bacterial cells. So these sludge granules will form. Some of them will float. Most of them will come down and settle in the sludge blanket here. So over time, the sludge blanket's thickness will increase. And because it is an anaerobic reaction, there is formation of methane and CO2 gas also. So these are sludge granules. So over time, there is formation of gas also. So gases will be at the top and it will be collected and it will be released through a gas cap. So this is the working of a upflow anaerobic sludge blanket. So it is a very simple terminology. Upflow, the water goes from water to top. So there is the flow direction is upwards, so upflow, and there is anaerobic condition inside the reactor. So and because of the anaerobic conditions and because of the degradation of organic waste by bacteria, there is sludge formation. So the sludge usually forms a blanket at the bottom. So the sludge blanket is there through which the water will pass through. Now over time, as the sludge blanket's thickness increases, what happens is it will act as a filter. So whatever inlet solids are there, those will be filtered by the sludge blanket, and again its thickness grows even further. So whatever sludge is formed inside the reactor will also fall down, and also whatever inlet water solids are there, those will also form the sludge blanket. So next, we'll be going to the questions and answers section. So if you have any doubts, let me know now. Or we'll get to the next. So usually, sludge granules especially happens in anaerobic reaction systems. Can you hear me? Am I audible? Am I audible? Am I audible? Yeah. So sludge granules are formed in anaerobic conditions. It is not formed in aerobic conditions. So sometimes in anaerobic conditions, what happens is the sludge or the water is in the wastewater that is coming for treatment. Since we are not giving any kind of pre-treatment, it is just raw sewage which is treated here. So sometimes it will have solid particles, maybe like grit or sand. So over this, a layer of dead bacterial cells will get collected. So over time, what happens is more and more bacterial cells will get collected on top, and it will form a hard granule. So sometimes over this, on the surface of the sludge granule, there will be live bacteria also. So this live bacteria will continue the reaction of degrading organic waste, and after that, whatever sludge is formed, it will cover the top. Now, once this layer is fully covered, the next layer of bacteria will grow, and that will also form a sludge. So the granule will become bigger and bigger. So unlike in anaerobic processes, here granule is the sludge granule that is formed. It is very dense and it is also very thick. So it is almost like a solid. It's like a complete. So it's not because of filtration. It's because there is some granule, there is a grit or a sand particle inside the reactor. So on top of that reactor, the bacterial growth will happen and it will degrade the organics and it will form a layer of sludge. So over that layer, again one more layer of bacteria will grow and that will die and that will form a second layer. So on, there will be third layer, fourth layer and all of these. So these layers are very densely packed together. Okay? So those are sludge granules. So these are not formed in aerobic processes because there is constant mixing and aeration and stuff, and we remove the grit and sand in the pre-treatment and the primary treatment. So that will happen only in anaerobic conditions, especially in upflow anaerobic sludge mackets. So these sludge granules are formed. So they are highly dense, and once they form, they will attract bacteria on their surface. So anaerobic bacteria, and the degradation will happen on the surface of these sludge granules also. But inside it will be filled with dead bacterial cells and maybe grit particles or sand particles and the septum. Okay, so since we are out of time, maybe doing a few more questions. So the first question, start with following. Which of the following is the flow rate for rapid sand filters? First option is more than 10 meter cube per day per meter square. Second option, more than 100 meter cube per day per meter square. Third option is more than or equal to 120 meter cube per day per meter square. Which is the correct option? Yeah. Yeah. So since it is going to be a rapid sand filter with vacuum, so the velocity is going to be high, and it's about 120 meter cube per day per meter square. Second question. So the second question is, which of the following is a cheap technique to remove arsenic from groundwater? First option is ion exchange. Second one is slow sand filter. Third option is rapid sand filter, and the fourth one is clay filter. Do you think slow sand filter can remove arsenic? Huh? Huh? But arsenic is I mean, it's not so big, right? When it is in a soluble form. Then how will it remove? Yeah. So clay filter is the correct option. Yes. Mm. Next question. So BOD COD ratio must be higher than which of the following numbers? Or if you yeah. So if it goes below 0.5, then we cannot do biological treatment. So it should be at least 0.5. Okay, so since we are out of time, we'll be ending the session now. COD is always higher because BOD is limited by the amount of organic matter that can be oxidized by bacteria alone. So compared to bacteria, yes. So if there are no other questions, we'll end the session now. Thanks for joining.